We're getting ready to start looking at some of the gas laws, which are mathematical equations that are used to predict the behavior of gases. The gas laws that we use are based on what's called an ideal gas. An ideal gas is one where the following assumptions are reasonable. If we make these assumptions about a gas, then the behavior of the particles can be defined by random motion and pretty simple equations. So these are not, most of these are not exactly true, but we make these assumptions and then the equations were derived and we use those equations. We'll talk about when these assumptions are most valid here in a second. The first assumption is that the molecular size is negligible. In other words, this is just saying that the particles are very, very small. In fact, they're point particles with no volume. The volume of the gas is defined by the size of the container. And remember, we've said this before, that the particles are tiny compared to the space between them. The forces of attraction, we're talking about the attraction between molecules, molecule to molecule attraction. We're going to assume that it's negligible as well. All molecules are really attracted to other molecules, but in a gas that attraction is less, and by assuming that they're very small, that makes the attraction less, and that there's a lot of space between them, that attraction doesn't matter as much. So it makes the prediction simpler because the particles will be moving around randomly. We're going to assume that all collisions of the gas particles, both with the walls of the container and with each other, are elastic. That means that no motion or energy of motion is lost. One may gain and one particle may lose, but overall kinetic energy is conserved and none of it is converted to heat. The movement is random in straight lines. If they're bouncing around pretty fast and they're not really attracted to each other, this is pretty true. Average kinetic energy is proportional to absolute temperature. This is pretty much the definition of temperature, but the word absolute tells you that we need to use the Kelvin temperature scale. This is because the Kelvin temperature scale is based at absolute zero, which allows the kinetic energy to be directly proportional to Kelvin temperature. In other words, if I have some gas at 100 Kelvin and I warm it up to 200 Kelvin, the kinetic energy has exactly doubled. That is not true if we look at Celsius. If you take 100 Celsius gas and warm it up to 200 Celsius, the kinetic energy has not doubled. So these are our assumptions, and this is how we define an ideal gas. If a gas is in a situation where these assumptions are reasonable, you can use these simplified mathematical equations called gas laws that we're going to use.